Hey there, welcome back to chapter one. Welcome back to chapter one. Okay, that last video was getting really long, and so I wanted to just take a break, and that way you guys could just deep breath and start again. Now, the good news is the rest of chapter one that we'll be working with will not nearly be as long as that video, maybe another 20 minutes. So, okay, let's take a look at a couple of things here. What we, oh, and I'm not in the right place, hang on. Wait a minute. Hang on. I'm having trouble here. Measurement uncertainty. Okay. Maybe this is where I was before. Okay. So we now have measurement uncertainty, accuracy, and precision. So what are we dealing with here? This is going to introduce us to significant digits or significant figures. So first of all, we could say that counting is the only type of measurement that is free from uncertainty. So if I count them, I have one eraser, I have one mechanical pencil, I have one mouse. I know that. I know that I have one calculator. I could also look here and say, oh, look, I have 2 sheets of paper. I can count them. I know exactly how many I have. So if you can actually count things, then we aren't uncertain about them. We are very certain we know exactly how many we have. Let me put things back where they were. Okay, so the result of a counting measurement is an example of an exact number. We know that 5 pens are exactly 5 pens. We know that they aren't 5.5 pens or 4.9 pens, there's 5. You could say that there are 12 eggs in our dozen, right? And we know that there are 12 eggs. I'm not going to open it up and be like, oh, look, there's 12.5 eggs here, because that just wouldn't make any sense. It's something that we're counting. Okay, now there's a few numbers for defined quantities that are also exact, but this isn't all the time. There's only a few of them. So let's talk about when is a conversion factor or a defined quantity exact. Okay, so when is a conversion factor exact? Okay, and the first answer is within a system. So if you're in the metric system, for example, if you're talking about the metric system, 100 centimeters in a meter, 1 times 10 to the 9th nanometers in a meter, etc. So within the metric system, these are exact. Within our standard system, we'll call it, within standard system, they're also exact. So you could say that there are 12 inches in 1 foot. This is a defined exact quantity. There are 5,280 feet in a mile. Okay. There are, let's say, there are 4 quarts in 1 gallon. Those are exact values. Okay. Now, let's say, when is a oh, there's one more, and then there's an extra. We're just going to call this an extra one. And that's 2.54 centimeters is equal to 1 inch. Those are all exact. Okay. Now, when are they not exact? Okay. It's basically, except for this one that I just put down, 2.54 centimeters is 1 inch. They're usually not exact when they are between systems. Okay, so an example of that would be that 1 meter is about, pretty close, but about 1.0936 yards. Okay, or that 1 pound is equal to 453.59 grams. Okay, so these are examples where they're not exact and they will have significant figures. And we'll get to that in a minute. Okay. Okay, so now let's think about these. Okay, so measurement. Quantities derived from measurements other than counting are uncertain to varying extents. And that's because we can never look at something perfectly. Okay, these numbers are not exact. They might be very, very close to exact, but that doesn't mean that they're actually exact. There are always practical limitations. That might be your eye, like how good your eye is at looking at the glassware, or how good your eye is at looking at a ruler. But even within a tool, let's say that you have a scale and you've put it on your scale. Well, you all know from like a bathroom scale or the doctor's scale that different scales have different levels of accuracy, right? You might weigh yourself at home and then weigh yourself at the doctor's office, and it's not the same. And one is better, one is more close to exact than the other one, right? Okay, so those are kind of our practical limitations. So a measured number must be reported in a way to indicate its uncertainty. In general, when recording a measurement, you are allowed to estimate one uncertain digit. Okay, so let me sort of, actually, let me see, what do I have here? Okay, I think the next slide will show that. Okay, so let's take a look here. And this is a little bit hard to see, but let's take a look. So you can see, it's easier to see right here. Let me see if with this very fine pen, if I can, there we go. Okay, so you make your reading right here. The bottom of this, the bottom of the meniscus right here is where you make your reading. Okay, well, so if this is 20 right here, okay, here we have 20 right there, and here we have this 25 up here. So here we have a mark here and here and here and here. So that means 22, no, 21, 22, 23, 24, 25. Okay, so this right here is 21. And right here we have 22. And we can see that this measures in between. Now, is it 21.5? Is it 21.6? Is it 21.7? We don't know about that. We are certain of the 21 and uncertain of the 5, 6, or 7. So, but you couldn't just say 21 because you can see that this isn't 21 and you can see it's not 22. So you do have to guess. So I'm going to look at this and I'm going to say, I think this is 21.5 milliliters. Okay. Certain, certain, uncertain. Okay, now let's take a look at how to report that. So remember we had that before, okay? So we said that we had 21.5 and we were certain about these, but we were not certain about this one. Well, we need a way to communicate to other scientists that we're certain about the 21 and we're sort of okay about 5, but we have no idea what comes after that 5. Not at all. So what we do is we write it like this. And what this does is this tells other researchers that we have what are called 3 significant figures or 3 sig figs. Sometimes they'll be called significant digits. Okay, usually people just call them sig figs. Okay, so significant figures or significant digits. Okay, so let's look at how to count that. Non-zero numbers 1, 2, 3, 4 through 9 are always significant. Captive zeros, and that's a 0 in between here, those are always significant as well. Now let's take a look at trailing zeros. If you have a decimal point, then we say they're significant. Okay, they're not significant if they are a leading 0 out front or if there is no decimal point. So let's take a look at what this would be. So this one we have 1, 2, 3, 4, 5, 6, 7. This has 7 significant figures in it. Now this one's easy to see, 2 significant figures. All right, now let's look at the next one. We have 0.708. So here are our significant digits, the 7, the 0, and the 8. All right, now let's look at this next one. There's these zeros. Now you notice there's no decimal point in here. It's not in scientific notation. So that's the way the scientists are telling us that they think it's approximately 6,900. It's about 6,900. But we aren't sure. We don't know about those zeros because there's no decimal point. So we would say just these two significant digits. Now here's another way of showing two significant digits. 1, 2. All right, and even though sometimes people like, but 10 to the 8th, because this becomes 7, 1, 2, 3, 4, 5, 6, 7, 8. And I put that decimal point in the wrong place. Okay. Okay, well, we're not going to write it like that. And the 8 doesn't matter. It's just where it shows here. Okay, now let's look at another one. Here we have 6.59 times 10 to the negative 7th. So just as a review there, this would be 0.1, 2, 3, 4, 5, 6, 7. Okay, so this number here that I've drawn is the same as 6.59 times 10 to the negative 7th. And it has 1, 2, 3 significant digits. Here we have 8. Well, unless we've counted that 8, then that's one significant digit. Now, this is where things get tricky, I think. Here you have 0.00006. Because you could write this in scientific, see, when you were looking at these, none of these first zeros were significant. Well, none of these first zeros are significant either. So in this case, 6, that's the only one that's significant, one significant figure. Okay, now let's take a look at significant figures when we're doing calculations. Okay, so here we have, it says results from calculations are only as certain as the least certain number. Okay, therefore, in this first one, we have 14 times 5,789. We're only 2 digits significant here, which means we can't report everything. And so we round 81,046 to 81,000, and we're rounding that 0 down because the 0 here that I have in red is less than 5. Okay, now let's look at this next one. Erase this piece here so that you can see it better. You have 15 times 5,789. Well, now you get 86,835. Okay, and again, we only have 2 digits here, so we can only have 2 digits here. So we have to round that. Oh, look at that. My first mistake. Okay, this should be 87,000. Okay, I will change that in your slides. Okay, now here you can see these. So we have, in this next one, we have 3.890 divided by 13.8. And again, this is our lowest number of significant digits because there's 4 here, so there's 3 here, and we can only have 3 significant digits. So this 8 will round up. We get 0.282 or 2.82 times 10 to the negative 1. Okay. Now, when adding or subtracting, again, those will be fixed in yours. When adding or subtracting, we round the answer to the least number of decimal places. So that's a little bit weird. Here, we just pick the lowest number and we round to it. But when we're adding and subtracting, it's actually easier to see if we line them up. So see how you have 15.0 and 18? Okay, that means that we can only go that far. And one way of looking at it is to say, okay, well, I have 15.0 plus 18. So when you look at it, you're saying, okay, well, I'm only this confident. And so I add those up and that'll give me 33. And then there's your answer. But if I had 15.0 plus 18.01, then I'm this confident. And so that becomes 33.01 or 33.0. So the answer to the top one would be 33.0 and the answer to the bottom one would just be 33. Okay, now let's say that we have these values here where we have really, really big ones. Okay, well, if we convert this 1.48 times 10 to the negative 7, here we've got the 6 zeros. Okay, and then here we have the negative 8, so we'll have 7 zeros, 1, 2, 3, 4, 5, 6, 7. Okay, well, what happens here is we draw our line just like that. That 2 rounds down, and that's why we're ending up then with what we have that you see here. Okay, and that's how we do significant figures in adding and subtracting. Okay, while you guys are taking notes, I'm going to make a quick note to myself. So that I don't forget to fix those, so that you don't see them in your work. Okay. Okay, so now let's take a look at density of objects, and we're going to tie in significant digits a little bit here. Okay, so first of all, it says calculate the volume and density of our rebar. All right, now again, handy dandy calculator. If you don't have yours with you right now, pause the video and go get it. Okay, trust me, please don't use a phone. Even if you're at home, I can't control that, but I recommend that you not use it. I will be asking you to show work, even on tests, so that I know where you're getting your values. Okay, so let's take a look here. And okay, so we have a variety of things listed. First, we have a rebar mass at 69.658 grams. We have a final volume and an initial volume. Okay, so here's our initial volume here, and here's our final volume here. Okay, now what we need to do is we need to figure out the density of our rebar. So our step 1 that we're working with here says is the volume of the rebar equals the final volume minus the initial volume. So first we're at 13.5 milliliters. We drop our rebar in and the water level goes up. So the volume of the rebar is equal to the amount of change that we had there. Okay, so we have 22.4 minus 13.5. And the reason I stacked them like this is so that you could see our significant figures. So 22.4 minus 13.5, and we get 8.9. Okay, so 8.9. Now the water is in milliliters because it's a liquid, but the rebar is a solid. So this needs to be reported as 8.9 centimeters cubed. Okay, now we need to stop and think for a minute. This has 1, 2, this has 2 significant figures, and that's going to be important for our answer. Okay, now it says calculate density as mass divided by volume. So our density is going to be equal to our rebar mass, 69.95. No, that's 65. Hang on, sorry. 69.658 grams divided by 8.9 cubic centimeters. Okay, so I have 69.658 divided by 8.9. Okay, now what I get on my calculator is 7.826741573. Okay, but you are not being more accurate when you use all those numbers. What you're doing is you're saying, I'm this confident, except that you're not, because like we're just kind of squinting at our little milliliters here. We're not super confident about our volume. It's not in a special volumetric type thing. We only have 2 significant figures, 1, 2, which means we can only have 1, 2. So when we report our final answer, this needs to be reported as 7.8, because the 2 will round down, 7.8 grams per centimeter cubed. Okay, so that's kind of the process that you need to be going through when you're going to solve these. And there's one just like this in the recitation. There. Okay, now let's take a look at accuracy and precision. And this is a little tricky. Okay, precise means that they're close together. Okay, so these are close together. Okay, now you can argue, some people will say that you can be accurate without precise if your accuracy all rounds to the same thing, but that's not really the case. In order to be accurate, you have to be accurate and precise. So the thing is that each individual measurement can be accurate, but you need a whole bunch to be precise. So this group is precise. This group as a whole is precise, but each individual one is accurate. So the group can be accurate, but each individual measurement can also be accurate, okay? And then this group is precise. Now this grouping over here, we aren't accurate and we aren't precise. So precision is about repeatability, accuracy is about hitting the target. So let's take a look at something that might be a little bit more scientific. We have these 296 milliliter dispensers. Okay, that's really important. That's our target. Okay, so in order to be determining accuracy, we need to be looking at that. Now, let's take a look here. Our first one, 283.3, 284.1, 283.9, 284.0, 284.1. We're about, so when I look at my entire range and then from top to bottom and then divide by my range, I get a 0.282. You don't have to be able to do, I won't be asking you to calculate these error percents. Okay, so don't worry too much about that. Just sort of showing you where that comes from. So these are all very close together. Okay, so they are precise because they are close together. However, they're 12 milliliters off from the target. That's quite a bit. So dispenser number 1 is precise, but not accurate. Now let's look at number 2. So we've got 298, 294, 296, 297, 293. We're more accurate, but we're less precise. It's, it's a little bit of a wider swing. And so I would say, at 1.49%, I would still say that it's precise, but it's getting less so. Okay, and it's definite and not, so it's not quite there yet. Now, if we look here, 296, we're very close, very precise, and we're right on that 296. So this one is precise and accurate. Okay, now this one, for that 200 and at 1.49, I would probably still call this, we'll just call this less precise. It isn't imprecise, it's just less precise, okay? If it was wider swing, then it would be different, okay? And it's still not quite accurate. Okay, now let's look at some conversion factors. So in the last video, we talked about conversion factors within the metric system. And I gave you a couple of conversion factors within the standard system. And now what you're going to be doing is I want you to use these specifically when coming up with conversions between systems. So meters are metric, yards are English or standard, right? You got metric. Okay, and you'll notice here that the only one that is exact is right here. Okay, so this one is exact. And remember, exact numbers equal infinite significant figures. So you can ignore them. That's what that means. But all of these other ones, so 1.0936, there's 5 sig figs here, okay? And there are 5 sig figs here, okay? Now there's 5 sig figs on just about, yep, all of these. Okay, so each one of the ones I have listed here has 5 significant figures. Sometimes you'll see something, for example, a lot of times you'll be watching a video and you'll see them write 1 kilogram is equal to 2.2 pounds. I don't want you to use this. Why? It only has 2 significant figures. So if you're doing a calculation, I don't want you to use the one with 2 significant figures. I want you to use the one with 5 significant figures. Because which one do you think is going to be more accurate? Well, the one that's going to be more accurate is the one where you used all the significant figures. Unless, of course, you're dealing with something that doesn't have any figs as is. But so that's what I want you to look at. All right, let me see here. Okay, our next slide is actually going to be working with some of this. Okay, so let's take a look at conversion factors and what we call dimensional analysis. And I showed a little bit of this before when we were doing the conversion stuff. Okay, so one thing, you don't have to, but some people really like to put that over 1, and that helps. And when you see something like this, you're going to multiply everything on the top and then divide it by everything on the bottom. So, well, what does that mean? Okay, so here you can see 34 inches, you've got your inches and centimeters, and they cancel. And where did we get this information? Well, here we have 2 significant digits, and here we have 2 significant digits. Okay, now let's look at something a little different. Here we're going from 4.78 miles to meters, and we're going to use 2 conversion factors. And the first one is going to be here. This 1 kilometer is equal to 0.62137 miles. And this other one, 1,000 meters to 1 kilometer. Okay, so now the way that you would find this on your calculator usually is that you would do 4.78 times, and I ignore the ones, so times 1,000 divided by, okay, and now see how you've only got one thing here, and again, you can ignore the ones, so we don't need parentheses, 0.62137, okay, and you'll get this long meso stuff. However, again, you only have 3 significant figures, 1, 2, 3. So you need to round to here, and that 2 will round down for 7,690 meters. Okay, now let's take a look at temperature. Okay, so temperature, here we have different temperature scales. So in the US, we're accustomed to the Fahrenheit scale. Absolute 0 on the Fahrenheit scale is kind of that temperature where nothing can get lower than that, okay? And water freezes at 32 degrees Fahrenheit right here and boils at 212 degrees Fahrenheit. The Celsius temperature, now they can't do anything about this absolute 0, but it's negative 273 degrees Celsius. But this water freezing thing, 0 degrees Celsius to 100 degrees Celsius. Now, every now and then it becomes a really, really, really big problem in our math that our temperature is negative. Okay, so that's not going to be a good thing for our temperature scale to have any negative numbers, because that might mean that we would end up with things like negative volume or a negative pressure, which can't happen. Okay, so what we needed to do is we needed to set absolute 0 at that lowest possible value we could get, and it's 0 kelvins. There's no degree sign on the kelvins, it's just the K for Kelvin. But then we said that 1 Kelvin is equal to 1 degree Celsius. So the increment here is exactly the same. All right, so how we convert within those looks a little bit like this. All right, so I'm going to show you this, and then that's the last slide that I'm going to do really now. What I'm actually going to do is we're going to do some practice then. Okay, all right, so now here we go. We have, I have to turn on my annotations. Okay, so let's go ahead and take a look at what we have here. Okay, so it tells you how to go from Celsius to Fahrenheit, or Fahrenheit to Celsius, or Celsius to Kelvin, or Kelvin to Celsius. So there is nothing that will help you go directly from Fahrenheit to Kelvin. You're just going to have to go to Celsius in the middle if you need that. Okay, so let's say that the high for today is 75 degrees Fahrenheit. And I want to know what that is in degrees Celsius and what that is in kelvins. Okay. So first of all, let's take a look how I'm starting. I have 2 significant figures, so that might be important later. So I'm just going to make that note. Okay, so the first thing that I'm going to do, it doesn't really matter. Yeah, actually it does. I can't go from Fahrenheit to Kelvin, so I have to first go from Fahrenheit to Celsius. So what I do when I'm going from Fahrenheit to Celsius is I'm going to use this one right here. So I plug that in. Okay, I say that my temperature in Celsius is equal to 5/9 times my temperature in Fahrenheit, 75 minus 32. So now this is an important thing going forward. This 32 is exact. Okay, so don't consider it when you're working with your significant figures. Okay. So then again, I grab my calculator and I have 5/9 times, oh, you know what, I'm gonna do this the other way. I'm gonna say 75 minus 32 times 5 divided by 9. That's a little easier on my calculator. I have an old one, but I like it. Okay, now that gives me 23.88889, and it could keep going. But I can only have 2 significant figures here. So I will round this to 24 degrees Celsius. Okay, now our step 2. In our step 2, we're going to go from Celsius to kelvins. So we're going to use this one right here. And we say, okay, our Kelvin temperature then is our degrees Celsius, 24, plus 273. So that becomes 297 kelvins. Now this is really important. Kelvin temperature, the Kelvin temperature that you use is dependent upon how many significant figures you had. So this could be, depending on how many digits you have, this could be degrees Celsius plus 273.2 or degrees Celsius plus 273.15. Okay, so if you have 18.2, okay, then you would use this one. If you had 15.68 and you have those two, then you would use this one. So use the conversion factor for kelvins that, excuse me, terrible summer for allergies. Use the conversion factor that has the right number of significant digits in it. Okay, all right. Okay, so I want next to, and I'm actually going to stop sharing for just a moment. We're going to go back to that whiteboard and then we'll come back and talk about that a little bit. All right, so what we're going to do is first, you have to move things around on your screen if you've ever worked with that. So now what I want to do is I want to give you a couple of practice problems just to see. Okay, so one of them is the idea of density, volume, and conversions or dimensional analysis. So we're going to combine all of this in one problem. And unfortunately, or fortunately, chemistry involves a lot of math where we combine a whole bunch of different things instead of just one thing. So we could say that what mass of seawater with density equal to 1.02 grams per milliliter will fill an aquarium with dimensions (18 inches, 2.0 feet, and 3.6 feet. Okay, now what we need to do before we can do anything now is we need to convert. Okay, so the first thing that I'm going to do here is we're going to convert all of these to see how this is grams per milliliter. Our step 1 is going to be to convert everything to centimeters. because remember that a cubic centimeter is the same as a milliliter. Okay, so step one is to convert everything to centimeters. So first we have 18 inches. Okay, and we know that we have, whoops, I almost did it backwards. That's no good. Okay, I need inches on the bottom and centimeters on the top. And 1 inch is equal to 2.54 centimeters. So I say 18 times 2.54. Okay, and what I get here is 45.72 centimeters. And I'm going to go ahead and round for my significant digits at the end. I'll have 2 here. Okay, for each one of these. Now the next one I have here is I have 2 feet. Well, let's remember that 1 foot is equal to 12 inches. So hopefully I don't need to show that. You know that 2 feet is the same as, I don't know why I just did that on the calculator because I'm tired. 24 inches, this one I do. And that 3.6 feet is 43.2 inches. And that's just because it's a little easier to do here. So we have 24 inches times, and again, 1 inch for 2.54 centimeters. 24 times 2.54. And that gives us 60.96 centimeters. And then I get and then we have 43.2 inches. And again, the 1 inch goes on the bottom and 2.54 centimeters on the top. And so now I have 109.728 centimeters. Now my step 2 is going to be to find volume. And remember, the volume of a rectangular solid is length times width times height. Okay. So I can take all of these and I'm just going to multiply them together. So I get 45.72 times 60.96 times 109.728. Again, calculator. 45.72 times 60.96 times 109.728. Oh my goodness. And I get 305821.9432. Wow. Okay. So first of all, let's go ahead and we need to simplify that for our, we need to simplify that a little bit. Okay, so we can only have 2 significant figures for our dimensions. So this becomes 3, 1, okay, because the 5 is going to round up, but these can't go away, the ones before the decimal point. So then we end up with 31, and then we have to turn the rest into zeros. So 310,000, oh my goodness, cubic centimeters. Okay. All right, now our step 3 is to find our mass. Okay, so remember that if density is equal to mass over volume, okay, then mass is equal to density times volume. We had done this one once before. And the density here is 1.02 grams per mil times our volume here, 310,000 cubic centimeters. Okay. And the cubic centimeters and milliliters, remember, are exactly the same. So we're just going to be left here with grams. So we say 310,000 times 1.02. And now we can still only have two significant figures. So this becomes 316,200. And for two significant figures, this becomes 320,000 grams. Okay, now I'm going to sneak in a little thing here. This is a lot. You probably wouldn't talk about this many grams. It doesn't make a lot of sense, right? So that's why we would convert it. So I would continue this and I would kind of say, hopefully you can see this at the bottom of your screen. Your step 4 here is going to be to convert this gigantic number to kilograms. Okay, especially since we don't have a lot of significant digits. So we have 320,000 grams times, okay, and we know that there are 1,000 grams in our kilogram, and the 1,000 grams goes on the bottom to cancel that out, and this becomes 320 kilograms. If you've ever had an aquarium, the water inside is really heavy. All right, and I have one more practice problem to add, and let me actually go back to that slide. All right. See if I can get it to page back. Oop, that's not what I want to do. There we go. Okay, let's come back to this one just for a minute. I feel like this, this chart, while very complete, is actually missing a pretty important one. So come back to your notes for this and let's add something that'll make things a little bit simpler, I hope. Okay, so you notice here that you have liters to quarts, quarts to liters, cubic feet to liters, and tablespoons to milliliters of all things. One volume conversion that I think is really important is gallons to liters, because in the US, we talk about our mileage, our gas mileage is miles per gallon. But in Canada and stuff like that, they talk about it in terms of kilometers per liter. So one of the things that we really need is we need a conversion that'll take us from gallons to liters. So what we need to know is that there are 4 quarts in 1 gallon. And that's part of our standard or our English system that's used here in the US. Okay, and right here, we have this quarts to liters. Okay, so if 4 quarts equals 1 gallon, let's go ahead and figure out how many liters is in 1 gallon. And so you can create your own conversion factors like this. And so you would say, okay, well, 1 gallon times, put 1 gallon on the bottom and 4 quarts on the top. And that's how it will allow you to get rid of your gallons. Times, and then we can use this one right here where we have 1 quart, okay, and we have 0.94635 liters. Now the 4 quarts, the 1 gallons, those are all exact values. So these 5 significant digits are all we really care about. So let's create a conversion factor using our calculator for gallons to liters. Okay, so we have that 1 gallon times 4 quarts times, so 4 times 0.94635. And that is 3.7854 liters. And you can use the whole thing. So feel free, you can even do this. I won't make you determine this on your own. You can add this right to your slides, right to your paper notes to use on tests and things like that. That 1 gallon is 3.7854 liters. So that is everything that I have on the slides. Okay, so let me see here. Now, if you're taking this class with me in person, which would be great, I'm looking forward to seeing you all, then we'll be working on all of these together in class. If you're taking them, and I will be giving you then, when we're working in class, I will be giving you an answer key for them. We'll work on them together. It's sort of like your homework for the class. If you're taking this class online, you need to do this part on your own. Okay, this is the only part, these in-class math practices that are in the slides, this is the only part that you can work with another student. So if you, your recitations have to be your own work. They can't be done in partners. And your reading quizzes, your reading comprehension quizzes need to be done on your own. And of course, tests always need to be done on your own. However, if you're working with a classmate, this would be a great time for you to work together. Okay, so what I will do is about a day maybe before the test, I will release an answer key for this online for my online students. So go ahead and work through these. Again, they're sort of for you. If you want them before I release it to the entire class, then just take a picture of your information and say, hey, look, I did it. Work it all out by hand and send me a picture saying, I'm done, I did it. I'm not just looking for the answer key just for the fun of it early. And I will send it to you. Okay, so here we have this first page, and let me just go over these just a little bit. So it says convert each of the following to standard notation and then to standard scientific notation. Okay, and then identify correct significant figures for each problem. And for 1A and C, excuse me, show your answer to 3 significant figures. Okay, and so the ones that you're going to be rounding to 3 sig figs are 1 and A and C. Okay, and it's just for that practice. Okay, and now in this one, it says yeast converts glucose to ethanol. And what I want you to do is I want you to look at this. Now, I'm just going to give you a little bit of a hint here. For this slide, what you need to do is you need to go back and you need to look at what we talked about when we talked about the law of conservation of mass or matter, conservation of mass or matter. Sometimes you'll see it listed as both things. Okay, so if you can't remember what we did and the math that I did for that, go back, take a look at that, and answer this slide based on that. Okay, next, it talks about whether the following can be determined exactly or must be measured with some degree of uncertainty. So you're just going to go through here and say, I can find that exact, or I can find that with uncertainty. And remember when your values are exact and when are uncertain. Okay, now this one is just sig fig practice. Okay, so remember your rules for multiplying and dividing. And remember your rules for adding and subtracting. Okay, so go ahead and look back on those slides for this. Okay, now in a case like this one here, where first you start with subtraction and then you have multiplication. Okay, first find your significant figures in this part here for the subtraction, and then use your significant figures from this first part to determine your final significant figures. Same thing here, find your significant figures for this part here in parentheses first, and then find it in the second one. Okay, now again, this is kind of your in-class math practice for conversions between SI units. Okay, and so this is all metric system conversions that I showed you. You show your work the same as I did it in the lecture. Don't try to cheat and use an app. Okay, you have to show your work. Okay, and now again, these are going to be converting again, and you can use those the slide. Let me see, slide number 28. Oh, I say it right there. Slide 28. And that will help you go back and forth on these conversions. And now we have density, volume, and mass and density. Okay, and you can go back to the practice problems. I had some practice problems in the first video as well as in the second video for mass and density. Okay, and then last but not least, some more temperature practice. And that is it. Let me know if you have any questions, and I will either see you on Zoom, or I'll see you in lecture, or I'll see you in class. Bye.